Okay, so now we are switching gears a little bit after John has given you quite a lot of introduction about the theory, what the theory about statistics and especially Bayesian statistics is, and about what the fundamental principles are in estimating phylogenetic trees, like the continuous time Markov models, what the substitution processes are. So for this next short introduction, that session. Okay. Yes. It's okay. I'm going to talk to you about just giving a really brief introduction, what RevBayes actually is and what our motivation is. And then we'll really try to slowly start going through using RevBayes, learning how to actually use it, what the specific differences are. So originally, or almost originally, we started out with then having 8 people working mostly on RevBayes. That was Bastien Bousseau in Lyon, who was at the beginning also in Berkeley, and at that time Tracy Heath was also in Berkeley. Then there was John in Berkeley. Frederick Ronquist, who was my PhD advisor in Stockholm, so the two of us were working in Stockholm. There's Brian Moore at UC Davis, so really close to Berkeley. Michael Landers, who was then a graduate student in Berkeley, so really strongly Berkeley-focused group. And Nicolas Latillot, the only outsider who was in France, in Lyon, where Bastien is now at the same time. And then additionally now Will Fryman, April Wright, Mike May, so April started, and where's April right now? In southeastern Louisiana. Mike is still a graduate student in Davis. Will Pett is a postdoc with Tracy in Iowa. Lyndon Cockle at Louisiana, LSU, Louisiana State University, with Jeremy Brown. So there's a lot of people starting to develop new methods and new models in RevBayes, and it is expanding quite a lot. So our team is growing over time. And there's probably some more people that I'm always forgetting. I'll just do a little bit contributions. The first main question that we always have is which software do you actually choose if you want to run a phylogenetic analysis or any type of analysis? Like specifically, what are the questions when you choose a software? Do you have any ideas? You use which one? Mela? Mega. Use Mega. Why did you use Mega? What sort of was the motivation to choose Mega? It's easy to use. Are there any other criteria why you choose the software? So easy to use is obviously one important thing. It's free, usually, like if you can get it for free or someone has a version that you can use for free. Are there other reasons? It's fast. In most cases, that's quite an important reason too, yeah, so the speed of the software. Any other things that are important for a software? User-friendly. I think that's sort of the same as easy to use, user-friendly. You could also say the documentation, all that, sort of that's one big area. Exactly, I was missing that part. So it's really important that it actually has the model or does the analysis that you're looking for. And this is sort of the main 3 motivations that we had for RevBayes. First is, does the software run the model and analysis that we do? And in RevBayes, that's what we're trying to do. We are trying to provide a really large amount of different models, really flexible, so that you can actually apply it to so many different types of analysis. And this was also one of the reasons why especially John and Frederick decided to move away from Mr. Bayes, because there were so many new models added to it that this wasn't what Mr. Bayes was designed for in the beginning. And we needed a software that was flexible enough to actually, to be able to be extendable for future models, that we can do so many different types of analysis. The second part is, am I able to understand the software and use it? So is it easy to use? Do I know what's happening if I press this button, or am I able to understand what all these features are? That was the motivation of it. And is the software fast enough to give me the answer in a reasonable amount of time? And I tried to answer now all these three different questions, how we try to approach it in RevBayes to give you the idea why we have made these design decisions. So why we also were looking for a single software in RevBayes and not saying like, well, we could have still used MrBayes for some parts of the analysis and then written some other software to do other parts of analysis and so on. So the first one is you only need to learn one software. And this might be sort of one of the goals also for this workshop, that in the beginning it will be very hard because it's a complex and new software, but maybe on Friday you will learn that or say that I've actually now mastered how to use RevBayes in some area, and now it will be easier to apply and use it in different or other types of analysis too. So it's really just you need to learn how that one single software works. There's a lower chance of incompatibility. So if we actually use RevBayes to estimate a phylogenetic tree, we're guaranteed that we can also use that phylogenetic tree to do our macroevolutionary analysis. That there's no incompatibility between each single step between like different types of software. That's a big motivation. There's the possibility that we can combine different types of models. Like Tracy will talk a lot about that. With Emma, she will talk about that too. That there's different types of models and analysis that are then more jointly working together. You could like jointly estimate the phylogeny, diversification rates, morphological characters, divergence time, all of this together if you just have a single software. Otherwise, you always would need to estimate the tree first, then you need to calibrate the tree, then estimate diversification rates and so on. But in one software, you can do that jointly, which also means that the joint inferences, they are theoretically at least superior, because that means you're taking all of the uncertainty in one step of your analysis into account for the next step of your analysis. Instead of just saying, I estimated my tree and then I'm 100% sure this is a correct tree, and then I'm estimating divergence times, and again I'm 100% sure that these are the correct divergence times, which will never be really the case. So if we do it in a joint analysis, we can take all that uncertainty into account by marginalizing, for example, over the tree topology or over the divergence times if we are only interested in some morphological character. And the last part is more for the developers, saying that there's no redundant coding necessary. Like John said, this continuous time Markov chain, that is a model that is, or that stochastic process that is actually used in a lot of different types of analysis. So if we use that for DNA evolution, or if we use that for morphological evolution, it's always the same process. So we just needed to implement that once and not again and again and over. So there's a lot of code reuse. There's also the MCMC algorithm and how that works for different types of analysis. We just needed to implement it once, and all the additional features that we're always adding to it, those can be applied to all the different types of analysis. Data structures and so on. So it's really advantageous for us now to have this like really big library and software framework to use to so many different types of analysis. So how did we address all these three different problems that I first set up? Is there's the general and flexible model specification, so that we have a lot of the availability of common models, and that it will be extendable to future models. Not that in 5 years we're going to say, well, RevBayes will be outdated because we're not using the models that we use today anymore, so we need to write a different software. The next one is it easy to learn? So well-structured model specification, that they're explicit models so that you actually see all the assumptions that you're using for a specific model, and that there's documentation, examples, tutorials, and last, that it's actually fast and efficient compared especially to a competing software, similar type of software, and at least not slower than other types of software. The first part, as John also started to say, is that we use the graphical model design. So he also showed that this squared box with a solid line, that is always showing you that this is a constant variable. And on the left-hand side, we see this is the constant variable for R. And on the right-hand side, we see how we would write it in RevBayes in the Rev language, which is just the scripting language, how you interact with RevBayes. So you would say R, then the left arrow 10, that is how you instantiate the constant variable. Then you have, as a second example, you have the constant variable, then you have the arrow going towards the solid circle, and the solid circle always means that this is the stochastic node. So here we would write that L, and then the tilde and the distribution name, which means if you use the tilde, that always says this is going to be a stochastic variable. And stochastic variables are basically the parameters in our analysis that we are trying to estimate. So here, in that case, that also means we can see in the opposite direction of the arrows which variable or which parameter depends on which other variables. So here we're seeing that L depends on the constant variable R, that we see that R was the parameter of this exponential distribution. Then, as John also showed, is if we have this solid circle, but if we shade it a little bit, that always means that we say we clamp that variable to an observation. So always when we have an observed or in observations, observed data, we're clamping it to stochastic variables, and that variable is not changing through our analysis, but as a graphical model that's represented in this way. Then the next thing that we can also do is we present it as a dashed circle, a variable. That means that's a parameter transformation. So in the RevBayes syntax, that means we say L is colon equals, and then the exponential function of R, which means that's deterministic because there's nothing changing actually, or nothing stochastic in there. Every time that R changes, I directly can compute what the value of L is. So these are these small transformations that we are seeing a lot of types in our models, where we just need to transform variables because we need them in a different form. And one of the examples that is really important is, for example, the Q matrix. So once we know the stationary frequencies and the exchangeability rate, we can just multiply them together to get that Q matrix. So the Q matrix will always be represented as deterministic variables in our models. So these are the basic types of variables. They are really important to understand because you will see them all the time in RevBayes to then see what are constant variables, stochastic variables, or deterministic variables. And finally, we can also have the representation that we have this dashed box around a variable. That just simply means that a variable is repeated n times. For example, if we have 2n minus 1 branch length, then we would write that box and say, in the Rev language, for I in 1 to n, or 2n minus 1, depending on how many variables we want to create. And then we create exactly the same variable n times repeatedly. So this is just the shorthand visualization how we would draw it in a graphical model. And one of the reasons why I'm really talking about that so much is that in a lot of our tutorials we show you the graphical model, and it's very important that you think about the graphical model first to then think about how do I set up this model in RevBayes, or a little bit also vice versa. When you understand the graphical model, you know which sort of steps you need to take to set up the analysis, and maybe also if you know how or see the script that is setting up your model, maybe you're able a little bit to trace back what the graphical model is. And in the graphical model, you always see the dependencies between different variables, which variables are, for example, priors, hyperpriors, constant variables, and so on. So as a phylogenetic example, we use the GTR plus gamma model with different priors. So first we start with saying we have that dashed box, and we are creating 2n minus 3 branch length variables drawn from an exponential distribution. So this is really just to help to visualize, see what's happening there. The next part is we are drawing a uniform we use a uniform topology distribution to draw the topology and just say that the only variable that is actually fixing us is saying how many tips does that topology have. So that means that every topology with n tips has the same prior probability. Then once we have the branch length and the topology, we actually assemble the tree. So once these two are known, the tree is actually deterministic because it's just putting the branch length on the topology to give me my tree. The next step is that we are creating two different random variables drawn from a Dirichlet distribution. And a Dirichlet distribution is just a distribution that specifies a prior on a vector of values that sum to 1. So for example, our stationary frequencies always need to sum to 1. So those 4, that's why we create a random variable pi drawn from that Dirichlet distribution. We also use the same for the exchangeability rates, but there it should be 6 elements in that vector. That also sums to 1 because we always use these scaled matrices. And then once we have those two, we can compute the rate matrix deterministically from the exchangeability rates and the stationary frequencies. The next part of this model is that we are creating the proportion of invariable sites, and that is drawn from a beta distribution where you see here that alpha and beta, those two values from that hyperprior, are just set to constants being equal to 1. The next step is that we are also creating, using a log normal distribution on the alpha parameter of that gamma-shaped distribution for the rate variation. And once we have that alpha parameter, we can deterministically compute what the different rate categories of the sites are. And then finally, we are creating our sequences from that phylogenetic CTMC process, taking as arguments the tree, the rate matrix, our site rates, or the vector of per site rates, and the proportion of invariable sites. So this one would be the complete phylogenetic model for a GTR plus gamma plus I model that we just need to instantiate to RevBayes and then need to run it. The nice part about this, what you can see also if we go, for example, back, if you just wanted to use a GTR plus gamma model, we could just remove this part. Or if you just want a GTR model plus I without the gamma part for the site rate variation, you could remove this side and just say that all the site rates are equal. Or if you wanted to use a Jukes-Cantor model or an HKY model, you could just exchange that GTR matrix. So that really means that these graphical models have a lot of flexibilities. You can always add another layer or replace different subparts, which means that this gives us a lot of flexibility in the software to replace parts of the model. And so we are really able also in the future to use the same structure of the software for new types of analysis. So I hope that convinces you a little bit that this helps us to have a very general and flexible model specification. And with that, we also have quite a lot of different models available for you if you want to run different types of analysis. And as John mentioned, we probably have much more models than MrBayes implemented. And with other softwares, well, there's some parts that other software might have, which we don't have, but there's also a lot of models implemented in RevBayes that you can't find anywhere else. So the next part is then about the Rev language. It's actually easy to specify these type of graphical models. And the nice part is that these graphical models really directly relate to what you would type into the software to instantiate your model script. And so this plate here, so that dash box, would be just written as this for loop for I in the number of branches. And then you put into the curly braces, you say my branch length, and a square bracket I is drawn from the exponential distribution with my rate parameter 10, which I just used there. So it's a really one-to-one correspondence between these two different, between the graphical model representation and the Rev language that we're using in the software. Then the next part is that we're specifying our uniform topology distribution, just with a number of taxa. And the next is we're using psi. This is our tree. And we use the colon equal command again because we're saying this is a deterministic variable and pass in as the arguments the topology and the branch length. Then we create our substitution rate matrix here. We say that alpha 1 and alpha 2, they are vectors of 6 elements for alpha 1. So that's for the exchangeability rates. And that's 4 elements for alpha 2 for the stationary frequencies. So we are creating for the exchangeability rate, drawing from the Dirichlet distribution, that vector of 6 exchangeability rates that sum to 1. And for the stationary frequencies pi, it's a vector of 4 elements that sum to 1. And then we use the Fn GTR, so that's our function for the GTR rate matrix. So there's also a function for the HKY matrix, or the Jukes-Cantor matrix, and F81 matrix, and so on. There's all these different types of matrices that you can just use to create the different rate matrix. So you would only need to replace that little part in your model to use a different substitution model in the entire analysis. The next part is that we create then our rate variation for the sites. We're creating that the mean alpha is the value of the logarithm of 5. This is just that mean for that alpha parameter. And the standard deviation, we set it to that value so that we basically have a nice prior distribution on that alpha parameter that specifies the rate and shape of that gamma distribution. And then we are using the discretized gamma function. So this one was the one that John was showing to discretize the gamma distribution in the 4 different bins and computing the quantiles of, or the mean or medians of the gamma distribution where the rate and shape are equal to alpha, and 4 is actually the number of bins that you're using. So in RevBayes, you could also just change it to use 5 or 10 different rates, and it would work in exactly the same way. It would just run slower if you would use more categories. Then you specified on this side the proportion of invariable sites. So that just P inf is drawn, so the tilde from a beta distribution where the parameters are 1 and 1. And finally, you use the DN Phylo-CTMC where you pass in the tree, the rate matrix, the number of invariable sites, the site rates, and you say what type of data it is. And finally, you clamp what data you had to actually that variable. So on the left side, again, you have the entire the graphical model. And on the right-hand side, you have the complete script that will tell you this is my GTR plus gamma plus I model. And then you can start, you can start modifying it, but also with that script, you're really explicitly seeing which prior distribution and which sort of model assumption I've taken. There's no implicit assumption which prior I used on which other parameters, because you had to specify every single one of them. There's no sort of default values in RevBayes that we might have made for some analysis that might have worked for our data that might not be appropriate for yours. You always have to write your little model block like that, and there you directly see what were the assumptions someone has taken for their analysis. Then additionally, as you will see over the next few days, we have quite a lot of different tutorials in the entire manuscript that is compiled together. Some of the tutorials are missing actually in there. We probably just need to rebuild it. But it has way over 300 pages and covers a lot of things like the introductions, models of molecular evolution, inference methods, divergence time estimation, diversification rate estimation, gene tree species tree estimation, biogeography, and different continuous and discrete morphological models. So that was the part about is RevBayes easy to learn, and what I forgot additionally to mention, our motivation for that Rev language was that we try to use something that is very similar to R. And I would assume that a lot of you have probably used R or seen R before. So our hope with that is that RevBayes might be easier for you to learn because it doesn't look so different to how R looks. Then it's also that these models are very explicit. So in that sense, it's more easy to learn or see what someone else has done instead of just always wondering what is the software actually doing. And that is another motivation for these really explicit scripts. And we tried to work a lot on documentation, examples, and tutorials. Then about the speed of RevBayes. Originally, I did a small comparison to MrBayes and Beast. At that time, it was still Beast 1.8, and we used MrBayes 3.2, both with and without the Beagle library for fast computations, but only on a CPU, not on the GPU, to sort of have a benchmark. Because the main motivation or question behind that was, is RevBayes, with all these graphical models, complexity, and all that we're adding to RevBayes, does it make the software much slower? And in our first version, RevBayes was indeed much slower than other software, but after 1 or 2 rewrites, we found out that under the HKY model, where we just look at how fast is the likelihood computation per MCMC iteration, is that we are seeing that RevBayes is faster than all the others except the Beast with Beagle combination that was still slightly faster than RevBayes. If we use the HKY plus gamma model, it's Beast plus Beagle that was faster, but RevBayes was the second fastest. If we use the GTR and GTR plus gamma model, it's exactly the same type of pattern that we see. So what that means is that RevBayes is not necessarily slower than other software or not necessarily faster. Just for the likelihood computations, it's sort of in the same ballpark. The second part that we were looking at is not just the computation, how fast we're actually computing the likelihood, but also how fast are we to accepting or rejecting new parameter combinations. And the graphical model presentation actually helps us a lot to see which part of the model do we need to recalculate when only small parameters or small parts have changed. So we compared it again to the other 4 combinations of the software and used a tree proposal that changes the tree, so the nearest neighbor interchange and the node slide that just slides a node somewhere on the topology, mostly just changing branch lengths or node ages. And there we see that RevBayes, because it saves a lot of the computation that other software is doing, it is actually faster even than Beast with Beagle together in a full MCMC setting. But again, what I really want to say with that is just that RevBayes, still because of the complexity, is not slower than other software, so there's no concern that this flexibility is a burden for us. And additionally, you could also run RevBayes on a cluster if you have it. And you see that if you run it on a cluster and you use, for example, 8 cores, you probably get it like 4 times faster than if you just would use a single core. It really depends on the data set, like how large the data set is, and how good the cluster setup is, how much communication between different CPUs is necessary, like what the overhead there is. And in this example, I noticed that with 16 cores, you run it in an hour, or instead of 11 hours on a single core. So we are using that a lot on quite a lot of different clusters, like in Berkeley and Texas, in San Diego, in Munich now, and in Louisiana, where all runs fine there. There's a lot of these type of analysis that you will do now that could be run on a cluster more efficiently. So I hope that also convinced you that it's at least as fast and efficient than other software. And finally, as I showed to you before and this morning, we have all of our resources, so the general website, the code repository, the tutorials, help, and the mailing group. So if you go to the main web page, you find the list of different topics to look for, like the about, software, where to install and get it, the introduction, The documentation is where you can find the help, the tutorials, a little bit of the validation that we're doing for the software, the forum, and the citation. So for example, the software, we usually try to update the links that you can download directly the latest Windows and Mac OS version. And here's if you would install it directly from the source code, so if you're compiling it. I'm seeing that most of you are having Mac computers and some have, are all the other computers Windows, or does someone have Unix? Unix. 3 people with Unix. Have you installed this software? Or? Okay. Okay. Well, we're going to. I noticed this morning that I compiled it again end of last week and made a new release for this workshop, but the link was still to the old website. So for everyone else who has just downloaded it, you should do that again and be sure that the version says 1.0.5. So this is the most recent version. Yeah, then we have all the tutorials that I showed as well before about the different types, like divergence time estimation, diversification rate estimation, biogeography, species tree estimation, continuous traits, and model fit. And we have our user group. So there is also the there's also the website directly for the workshop, which I forgot to mention earlier this morning. Do you all have you all seen this one? This is also where we then directly link the tutorials that we are doing in that session. So to start now, what I want you to do is you need to download the latest version of RevBayes and check that you have version 1.0.5. If there's any problems with the installation, just ask me, Will, or Tracy now during that session, and we can help you to get started. And the first tutorial that we're now doing will be the MCMC intro tutorial to go through a little bit the syntax of RevBayes, but also to get you a little bit familiar more with Bayesian inference and Markov chain Monte Carlo simulation. Yeah.
I mean, I have it working with the regular version, but I did try to compile the MPI version.
All right.
I swear it worked right after I compiled it, but when I came back and tried it again, I get this kind of strange error.
All right. I think you just need to copy it somewhere in a different directory. I noticed that before on this machine. If it's like too far nested inside, I think that the MPI has a problem with that.
Okay, so it's just the location of the...
Yes, I think so. Yeah, you should try to copy it on the desktop and try it there if it then runs.
Okay.
Yeah.
Sebastian, you say version 1.05?
Yeah.
Okay. From August 4th.
Yep.
That's the one. Okay.
Yeah, yeah. So the first tutorial that we are doing that you should find from the link is called this Introduction to MCMC Simulation using the simple binomial model. And this is also exactly the model that John was using earlier this morning to introduce some probability theory and maximum likelihood and Bayesian inference. All of our tutorials will have in common that they will provide you a lot of the background theory and information, which is mostly for reading at home or understanding more about it. So I won't really go into all of these details, but for example, it explains again what the likelihood function is. It also shows again that this was the likelihood, so we have Bayes' theorem here. This is our posterior distribution that we're interested in. We have our prior distribution, and then the marginal likelihood, that is this normalizing constant in this example. And the next part here is that we also show again what John drew on the whiteboard. These are different types of prior distributions depending on which parameters we use on that beta distribution. If we use a beta with 10, it's really centered around 0.5. If we use a beta distribution with 0.5 and 0.5, then we really get that U-shaped prior distribution. Or you could just look it up on Wikipedia or plot it in R to see how that beta distribution changes. And the graphical model to that example tutorial will be that we have two parameters, alpha and beta, that are the constant parameters of our probability, the theta parameter in John's example, and that is drawn from a beta distribution. We have n, the number of coin tosses, and then it's a binomial probability, how many coin tosses were actually heads. So I will continue to go through that tutorial to really explain what is happening, and also will show how it works. You can mostly try to just follow me here and then try to repeat it afterwards. And yeah. An important part also is that you will see all the blue boxes, as it's mentioned here. Blue boxes are the parts that you should type into the RevBayes console and try to execute those parts. All the other parts is just text explaining what is happening. And what we want to do here again is we want to learn and understand how the Metropolis-Hastings algorithm is working. And the Metropolis-Hastings algorithm, the basic structure for it is that we start to generate initial values for our parameters. That's the first step. For example, for the parameter p, our probability that it's a head or tail, we generate a starting value in our MCMC. Then we propose a new value. Let's say the first one that we used to initialize was 0.35. And then we propose a new value. Let's say we add 0.7 to it. So that means it's then, we add 0.07 to it. So it would be then 0.42. And then the next thing is that we calculate the acceptance probability once we have proposed a new parameter value. The acceptance probability is the probability of the data for that new parameter value divided by the probability of the data for the old parameter or the current parameter value times the prior probability of the new proposed parameter value divided by the prior of the old. So that's basically the posterior ratio, so the posterior probability of the new proposed value divided by the posterior probability of the old parameter value times, and this is the Hastings ratio, so of the proposal density times the probability of moving from the proposed value back to the original value divided by the probability that we started with the original value and proposed our new parameter value. And usually you will see in these cases that will be a symmetric proposal, so the probability of proposing a new value or proposing it backwards will be the same, so that part will cancel off in many cases. This is really just to explain to you how that algorithm works. So once we have our acceptance probability, then we generate again a random uniform number between 0 and 1 to decide if we accept our new proposed value. And if that random number is smaller than our acceptance probability, then we accept it. So if our acceptance probability can be at most 1. You can imagine or understand that a little bit like if the posterior probability of the current value is smaller than the proposed value, then this ratio will be larger than 1 because that part will be larger than this part for the posterior probability of the old value. So this ratio will be larger than 1. And if the Hastings ratio, the proposal densities cancel out, our proposal or our acceptance probability will be 1 because we're saying the minimum of those two numbers. So we're always going to accept steps to better values or parameter values that are going to be having a larger posterior probability. But if we imagine the proposed value has half the posterior probability of the original value, then we're only going to accept it with a probability of 0.5. So in maximum likelihood, you would always only going to accept parameter values that lead to higher likelihoods than you previously had. But in Bayesian inference, in these MCMC algorithms, it's a stochastic algorithm where you have some chance of actually going downwards to values that had a lower posterior probability because we need to explore the entire MCMC, the entire parameter space. Then we record the values of the parameter values, and we go back to step 2 and just repeat that as many times as we wanted to run our MCMC. Is that a little bit too small in the back, or is that fine?
Is that you here? Can we open that?
Yes.
Yeah.
That should be if you click on this tutorial here. If you just download this one, that should be exactly the one that I was showing. So I can just start on my computer RevBayes directly by typing RB in the terminal in the command line. For you, that might be possible if you either edit the path to RevBayes to your path variable, or if you copy it to RevBayes to use a local bin or somewhere so that you can start it directly. If you have problems to start it, again, just ask Will or Tracy. They definitely might be able to help you. So the first thing in RevBayes that you also will see here, it's really similar to R. If a line starts with that hash symbol, that means that's just a comment. And it's really good style if you write your script to add a lot of comments to remember then in a month what you were actually doing. Because I'm always forgetting what that actually was. This case, I might be able to remember. If you also put the hash symbol somewhere in the middle of a line, that just means everything to the right of it is a comment, only the first part will be executed. So the first thing that we're doing here, we say that we had 100 draws or coin flips. So in RevBayes, you can also just then type in n. That says you have the value of the variable n is 100. The next thing is that we are saying x was our observation was 63 heads for these draws.
Can everyone see okay, or should we turn the light? Or should we make your copy? Yeah, like this light that's like right on the
Is that better? Mm-hmm. Okay. So the next part is we're specifying now our prior probability. So we're going to say alpha is equal to 1 and beta is equal to 1. And then we initialize that p, our parameter, is drawn from a beta distribution. So we use that distribution to generate a random starting value of our MCMC. We say we just wanted one value. Take alpha and beta, and that's returning a vector, so we need to get the first value. So if I did that, I actually got a value for p of 0.99 and something. If you did it, you should definitely get a different value because it's different random numbers that we're generating. So we have done the first step of the MCMC algorithm, that we generated a random starting value. The next thing is that we are specifying a likelihood function. And the likelihood function in RevBayes is, we say it's a function. The return value is a positive real number. And we call it the likelihood, and as an argument, we pass in p, so our probability of successes. And the likelihood is calculated as the binomial probability. And we're saying that we're not using the log in this example, although John said that in practice we will always use the log just for making the calculations easier. So I'll just copy that function into RevBayes. We're doing something similar for the prior, but there we're using a beta prior distribution. So where we compute the prior probability as the density of the beta distribution for our parameter p with prior parameters alpha and beta. And that is all the parts that we needed to specify. So we have the likelihood and we have the prior. And with those two, we can actually calculate what the acceptance probability is. To start then actually monitoring of writing variables, what we're going to do is we are writing the header of a file where we're storing the values. So in RevBayes, we use this write function, and the first header for the column will be the iteration, which iteration that currently is, and then the second one will be the name of the parameter, and then we're just ending it with a new line, and we're calling the file binomial_mh.log. So in RevBayes, if you don't know where that file was actually generated, you can always use, like in R, the function getWD, which is for get the working directory. Well, that's actually printing out some debug statements still for me. So it's an user's Höner, which means then I could just check, and in my users directory, there should be the binomial_mh.log. So that's where it created that file that just has the names for those two columns currently written in it. The next line that we're writing is that for the iteration 0, so for our starting iteration, we always start the MCMC at iteration 0. We start that one and write the parameter value, the current parameter value, into that file. And here it's important that we say append true, so that it's always going to append into that file. So then the next thing is what we're going to do in RevBayes is we're going to write now the Metropolis-Hastings algorithm. So we're specifying what the printing frequency is, because quite often we don't want to print every single iteration to the file, because that would mean that we just have a lot of different values in our file. And in the MCMC, consecutive iterations have a strong correlation, because if you didn't accept a proposal, the value would be exactly the same as before. And the only reason that we're actually not storing all these values into a file is that we don't have an unlimited amount of disk space. Otherwise, we would do that. Here, I'm really doing that to show you this is also what you're going to do in real analysis in RevBayes. So here, you will really start to learn what is happening under the hood and what are these parameter values or these arguments, what are the meanings of those. And yeah, please interrupt me if you have any questions about what some parts are meaning or what's happening there.
When you connect strings with a comma, it's just doing tabs instead of tabs? Iteration, comma.
Yes, by default. So there's different features in RevBayes. I could just type in the name of a function, and that will print out what the function is, so what you can pass in any type of object, and then it has the argument a string for the file name, a bool if you want to append it, and the string for a separator. Here you don't actually see what that separator, what default value that is. So if you type in question mark and write, you get a little bit more information about it. And then, yeah, that is a tab, which you don't see because it's just white spaces. But usually you would see what the default value is. And by default, the separator between different values, different strings there is a tab. Which you could just specify a comma if you wanted to, and then you get a CSV file or something like that. Okay, so back to setting up our Metropolis-Hastings algorithm. So first we are setting how many repetitions or iterations we're going to do. And in this simple example, we're saying we're doing 10,000 iterations of our MCMC algorithm. Then we are going to start our loop and saying that we're going to repeat these steps 2, 3, 4, and 5 10,000 times. So we're doing that in this for loop. So that means that for rep in 1 to the number of repetitions, so rep is our index or the variable that will be just counting in which iterations we currently are. So it will change from 1, 2, to 3, to 4, to 5, until it is at 10,000. The next thing is that we're computing a new value for our parameter p. And in this case, we're just drawing uniformly a new value. So we're proposing uniformly, without remembering what the previous value was, what our new parameter value should be. So this is our proposal for the next value. And then we compute the acceptance probability. And if you remember, that was the ratio of the likelihoods and the ratio of the prior. So we compute the likelihood to ratio here times the prior ratio. And because the proposal probabilities were completely independent of the previous values there, and every value had, in my case, the same probability, so the proposal ratios were canceling out. So we're computing R. And then we're drawing our uniform random variable, or our uniform random number, to say if we're going to accept that new parameter value. So if we're going to accept it, so if u is smaller than r, we're setting p, our parameter value, to our new proposed parameter value. And then finally, we're going to say if the current repetition is divisible by the printing generation, so if it's divisible by 10, then we're going to write into our file the current parameter value. And then we close our loop of the MCMC. Yeah, that didn't quite work. I guess if you have problems copying and pasting all of it, one possibility that is helping for this part is Yeah, there's a problem with the PDF viewers that if you copy and paste it, it doesn't really work. Let me just... You're doing it from the text file. Oh, that might be also...
Yeah, in that case, at the presence of that comment is throwing in a... It's closing the loop, the for loop, when the comment's in place.
Okay. If you remove the comments from the loop, then it should be working. Let me.
If it closes the for loop too early, do you have to go back to the beginning of the for loop to redo it all, or can you?
Yeah, if it would close it too early, yes, then you have to do that.
So you can't quit the for loop without quitting RevBayes.
Well, in that sort of the problem right now is that it thinks that you're still in a comment,
Yeah.
so you can't quit the comment.
Right.
So yes, you have to just yes. So I also have already written down the entire script here, which I probably can just copy that part here and remove the comments. If I remove all the comments in my for loop, we didn't really did that part. There's nothing to reject. Okay. So now it's running the loop because I'm seeing that it's just waiting there. So what we can do next is if you have installed Tracer on your computer, you should, you can just take the output file, the file that it is creating, and then drag and drop that into Tracer, where you're going to see, it's going to say the state, so it ran 10,000 iterations, had a burning automatically set to 100. You see that the mean parameter estimate in my case here, let's remove this one. So the mean parameter estimate is 0.628, so it's really close to what John was saying would be the maximum likelihood estimate, because we had 100 coin flips and 63 of them were observed as heads. So you can look in Tracer here at the mean. You can look at the standard error of the mean. It also shows you the 95% HPD. So this is your credible interval that you're going to use. That is where the true parameter value in this example should be. You could also look at the trace. This is actually where you see how the parameter in your MCMC was changing. So the important message of this tutorial was this really simple part that we were doing now, that is an entire MCMC algorithm. So you should really not be scared about MCMC, and it showed all the important steps of an MCMC algorithm. You were using a move by just proposing new values drawn from a uniform distribution. You had a monitor, so you were writing into a file the parameter values. So it has all the ingredients of a full Bayesian MCMC analysis.
Is there a way to use a cursor to the arrow?
Are you using Windows? For Windows, it's not possible. For Mac, it is. Yeah, there's something about the terminal that is, yeah. This one? So the easier part to, instead of really copy and pasting everything, would be if, so I have the script stored, I have it in my RevBayes tutorials directory. And I could just say, if I open RevBayes here, I can say just source. It's called scripts, and what was the name of it? Binomial. MH algorithm.rev. So I could just type in that command, and then it would run the entire script as well. So especially for the later analysis, it's the best way is always if you work directly in a text editor on that script, and then in RevBayes, you're just typing in the source command that would do exactly executing all the steps in your analysis.
Is the indentation important?
No. Indentation in RevBayes doesn't really matter. So white spaces usually don't matter, except if they're actually in strings. Okay. So the next step here in the next part of this tutorial would be that instead of where we directly did our proposing a new value, we call our move as a function, and where 1 would be the weight of the move, where the weight means how often we're going to use that move. And the function for this move is then all this part where we, in the uniform move, we proposed a value uniformly drawn from between 0 and 1, computing the acceptance probability, accepting or rejecting it, and that is it. So if I would put a weight of 5, that would mean in every iteration that loop would be executed 5 times. So I'm proposing 5 new values every time and do 5 times accept and reject before I'm going to the next iteration. That is the uniform move. And then the other move that you will see a lot of times in a lot of our tutorials, so it's a very popular move, is the sliding move. And the sliding move works by you take your current parameter value, you draw a value from a normal distribution centered at 0, and propose and with a standard deviation of delta. So that just slides it to the left and right of the current parameter value. And then you calculate again the acceptance probability in the exact same way as we did before. So I would suggest that you're just following and try that second part through. And we had planned so that there would be coffee break now. So I would suggest that you'll just, if you want, grab a coffee, or otherwise continue a little bit through that tutorial. And we'll see then maybe at 3:30 to continue a little bit more with the next tutorials.